My name is Dr. Esther Trufan, and in this video, we're going to explore a few of the details associated with the Bohr model. By definition, the Bohr model will refer to the very discrete and specific wavelengths of light that are associated with electron transitions. Electrons are moving around on orbitals around the nucleus, and as they move around in those orbitals, their energy is assumed to be constant. However, as they jump up from a lower orbit to a higher orbit, they absorb energy, and that energy is associated with a very specific number, and that will be the same in both directions. Because when that electron falls down into its original orbit, the energy that it picked up in the process of jumping up will be released. So the only difference will be the direction in which the energy is communicated, but not the value of the energy that is used. When it comes to experimental details, we need to distinguish between absorption and emission spectra. If we shine a continuous spectrum of light on a sample that contains a small amount of hydrogen, then it will absorb of all those different types of radiation only a few wavelengths. And so those wavelengths will appear in our continuous spectrum as these dark lines. In the emission spectra, we're looking at the photons emitted by electrons falling from a higher energy orbit into a lower energy orbit. And so instead of seeing the continuous electromagnetic spectrum, we see it as a dark space because there is nothing but the photons emitted by the relaxation of the electrons. And so we only see a couple lines. These lines are in the same positions that we had the dark lines in the continuous spectrum, in the absorption spectrum of the hydrogen. Now, I am focusing my presentation mostly on hydrogen because the Bohr model only applies to hydrogen. For all other atoms that have more than one electron, it only works through approximations. The electrons are moving around in orbits. Those orbits are going to have different energies associated with those. And the energy of each orbit can be easily calculated using this formula. Here, E stands for energy, N stands for the number of the orbit that we're looking at. This is equal to, and here we have a negative sign to indicate the attraction between positive and negatively charged particles. Here we are talking about electrons being attracted to the nucleus. R is the Rydberg constant, which is 1.097 times 10 to the 7th per meter. H is Planck's constant, and C is the speed of light. These constants never change. The only thing that changes is the value of N. If we move from orbit 1 to orbit 2, the value of N associated with energy will change, and the value of N here will change. It's simply going to be squared. When it comes to electron transitions, if we're able to determine the energy of one orbital and another, then the difference in energy between the two can also be calculated. If we complete these calculations, we find that the difference in energy between orbit 1 and orbit 2 is going to be the highest, and then orbit 2 to orbit 3, and then orbit 3 to orbit 4, and so on. These will get increasingly smaller. So much so that even if we take an electron from orbit 2 to the outermost orbit of the atom, it still will not require more energy than it did require to move the electron from orbit 1 to orbit 2. And the same kind of process is repeated for all other orbits. This energy difference can also be connected to the frequency and the wavelength associated with the photons that are either emitted or absorbed in the process of the electron transitions. Balmer was the first to identify the relationship for visible light. However, Rydberg is the one who expanded it to include all types of radiation that are impacted by the electron transitions. The final expression that we have then connects the inverse of a wavelength and says 1 over lambda equals R, which is Rydberg's constant, times, and in parentheses, we have something that probably reminds us to the expression that allowed us to calculate the energy of the different orbitals. That is a 1 over n1 squared minus a 1 over n2 squared. N1 will always be the lower energy orbital, and n2 will always be the higher energy orbital. Here is a problem that requires us to use this information to complete a calculation. We are provided with one of the wavelengths from the hydrogen emission spectrum. It is a red photon of 656 nanometer wavelength. The first thing that we will have to do is convert to our base unit for wavelength because all our calculations require the use of base units. Here we start with the 656 nanometers and we use our prefix conversion factor. On the bottom, we place a 1 nanometer, and on the top, we have 10 to the negative 9th meters. This will result in 6.56 times 10 to the negative 7th meters. Once we have this number, we are ready to move into our Rydberg's expression. So in step 2, we're going to calculate N2 if we know that our lower energy value is N1 equals 2. So from here, we're going to say a 1 over 6.56 times 10 to the negative 7th meters equals, the Rydberg's constant is a 1.097 times 10 to the 7th per meters times, and in parentheses we put a 1 over 2 squared minus a 1 over n2 squared, and this is the part that we don't know. It is a one unknown equation. To simplify it further, in the first step, we're going to divide both sides by the Rydberg constant. This will allow us to cancel the per meter on the left side. We are going to have 0.139 be equal to 1 over 4 minus 1 over n2 squared. I prefer to work with positive numbers, so I will move the 1 over n2 squared to the left side, and I will move everything else to the right. 1 over 4 is 0.25. I simply converted the fraction to a decimal. And the positive 0.139 from the left side will become negative 0.139 on the right side. This tells us that 1 over n2 squared is equal to 0.111. From here, we can determine the inverse of both of these numbers. And 2 squared is equal to 9. And from here, we're going to square root both sides, and we find that N2 equals 3, which means that the emission of the red photon is associated with the relaxation of an electron from N3 to N2.